And I am Akisha Sibungaras.
And we are your reporters for today. Good morning once again. We have all known from our elementary days and high school days that atmosphere is a blanket of air that surrounds Earth. It protects Earth from ultraviolet rays and makes all life processes here on Earth possible. So today, we will be discussing deeper into the composition of the atmosphere. What are the gases involved and its composition, its layers, and how it would affect us humans or organisms living here on Earth. So, we have chapter 1, Earth and its atmosphere. So, in order to guide everyone, we have our author tips. At the end of the lesson, the students will be able to describe how the Earth's atmosphere evolved to support life on Earth. Compare and contrast the atmosphere of the other 7 planets in the solar system to the Earth's atmosphere. Interpret a weather map to identify different weather systems and cultivate a sense of appreciation for the complexity and beauty of the Earth's atmosphere through writing a short dedication letter addressed to the Earth's atmosphere. So, the atmosphere and the scientific method. We often hear the word scientific method, but let us really know what does it mean or its definition. So, scientific method is crucial to atmospheric science, particularly in improving weather forecasts. It's the foundation for advancements in many fields, including atmospheric science. So, scientific method involves posing a question, forming a hypothesis, making predictions, and testing those predictions. So, in scientific method, we pose hypotheses, which are equivalent to possible answers, and to test those, or to know if our hypothesis is correct, we must test that. So, we were discussing about scientific method. So how is it related? Or how is scientific method applied in atmospheric science? So hypotheses must be validated through quantitative tests. Weather instruments provide data to quantify atmospheric behavior and test predictions. So here's a fun fact. We only have one atmosphere and one Earth. Therefore, testing hypotheses of scientists is impossible because we cannot multiply or have another atmosphere or another Earth to test our hypothesis, right? So, how did scientists or experts use scientific method in atmospheric science? So we have, here now comes in the invention of technology. Well then, thanks to technology, theoretical models now simulate atmospheric behavior using physical laws. These models allow for repeated testing and forecasting. They can recreate past weather patterns, increasing confidence in future rigorous testing of scientific method. Even if scientists were not able to recreate another atmosphere or another Earth to test their hypothesis, thanks to technology, we are still able to test our hypothesis through recreating past weather patterns, making predictions more accurate. Then we have the overview of the Earth's atmosphere. So we all know from our elementary days the solar system, and the center of our solar system being the sun. So the sun's radiant energy is the primary source of warmth for Earth, with an average distance of 150 million kilometers or 39 million miles. Earth receives enough energy to drive atmospheric processes and maintain a relatively mild average surface temperature of 15 degrees Celsius or 59 degrees Fahrenheit. So here, it is being said that the average distance of the sun to the Earth is 150 million kilometers or 39 million define upper limit to the atmosphere, it just slowly fades into space. So the early atmosphere, or the first atmosphere. So let us know if the atmosphere that we have now is the atmosphere that was present 100 million years ago. So we have approximately 4.6 billion years ago. So the Earth's initial atmosphere likely consisted of hydrogen, helium, methane, and ammonia. So if the early atmosphere was composed of these gases, what happened to our early atmosphere? So this early atmosphere was likely lost to space due to Earth's hot surface. So water vapor and carbon dioxide were the main components of the second atmosphere. So our first atmosphere evaporated to the universe due to Earth being hot. So now we have a second atmosphere, and our second atmosphere was mainly composed of water vapor and carbon dioxide. So as millions of years passed, the constant outpouring of gases from the hot interior, known as outgassing, provided rich supply of water vapor, forming clouds and leading to rainfall. So the first atmosphere was lost due to the Earth being too hot, and the second atmosphere was created due to outgassing, which is defined as the outpouring of gases from the hot interior. So it is also believed that when Earth was very young, some of its water may have also been deposited by meteors and comets. So we all know that meteors and comets, some of them are made up of ice. So when debris or meteors land to Earth, those icy comets and icy meteors would melt and pour into or become Earth's water. So rainfall also led to the formation of oceans where large amounts of carbon dioxide dissolved. So carbon dioxide was then locked into carbonate sedimentary rocks such as limestone through chemical and biological processes. As water vapor condensed and carbon dioxide increased, the atmosphere became nitrogen dominated. So our second atmosphere, which is dominated by carbon dioxide and water vapor now, is slowly changing into the atmosphere that we have now. So how did it change? So our carbon dioxide, due to raining, the carbon dioxide was locked into carbonate sedimentary rocks, and our water vapor is condensed and decreased, which now led to our nitrogen-dominated atmosphere of the present. So oxygen began to increase slowly through photodissociation. So photodissociation is where solar radiation split water vapor into hydrogen, which escaped and oxygen. After plants evolved atmospheric oxygen, which is current levels several hundred million years ago. So from our first atmosphere to our second atmosphere, which was dominated by carbon dioxide and water vapor, we now have our nitrogen-dominated atmosphere. And it is being said here that the levels of abundant energy source. It exists in all three states of matter in the lower atmosphere. Then we have carbon dioxide. So carbon dioxide is approximately 0.04% of dry air. It enters the atmosphere through decay, volcanic eruptions, respiration, fossil fuel combustion, and deforestation. It is removed by photosynthesis, chemical weathering, and ocean absorption. So ocean is a large reservoir containing more than 50 times the atmospheric CO2. So concentration has risen significantly since the Industrial Revolution, primarily due to fossil fuel or combustion. So a key greenhouse gas contributing to global warming ice core data shows pre-industrial levels were around 280 parts per million and are now over 410 and rising. So we have here the concentration of greenhouse gases before. This was reported by the ice core data. We have 280 parts per million and now it is over 410 and is still rising. We have here the figure. In 1950, it was over 315, but now in 2010 or 2022, it is rising now. Then we have methane. Concentration has been rising from sources like plant, decomposition, termites, and livestock. We have nitrous oxide. Concentration is also increasing from industrial processes and soil bacteria. It is destroyed by ultraviolet light. Then we have fluorocarbons or CFCs. CFCs were previously used as propellants and refrigerants. CFCs have been important effect in our atmosphere. They not only act as greenhouse gases to trap heat, but also play a part in destroying the gas ozone in the atmosphere. And the using of CFCs were phased out by the Montreal Protocol. It was replaced by hydrofluorocarbons, which are still greenhouse gases. Then we have ozone. It is found in the stratosphere where it absorbs harmful ultraviolet radiation. So it is a primary ingredient of photochemical smog. Smog is a word which irritates the eyes and throat and damages vegetation. However, it plays a crucial role because it shields plants, animals, and humans from the sun's harmful ultraviolet rays. So when CFCs enter the stratosphere, ultraviolet rays break them apart and the CFCs release ozone-destroying chlorine, fading the ozone hole over So, in order for us to appreciate how large this number is, we can compare it to the number of stars in the universe. So, to determine the total number of stars, we multiply the average number of stars in the galaxy by the total number of galaxies. So, we have 5 multiplied to the 10 to the 11, and we have 10 to the 22nd stars in the universe. So, therefore, just a few breaths of air contain about as many molecules as there are stars in the known universe. So this says that in one breath of air, there is, or air contains about as many molecules to that of the stars in our universe. So exhaled molecules eventually mix thoroughly throughout the atmosphere. Due to the vast number of molecules, it's highly likely that we inhale molecules previously exhaled by people from the distant past. So this illustrates that we all share the same atmosphere. So we now have the vertical structure of the atmosphere, which will be discussed by Ms.
Good morning, everyone. Today, I will be discussing the vertical structure of the atmosphere. So our atmosphere is divided into different layers based on temperature changes, gas composition, and electrical properties. But before we go into these layers, it is important to first understand air pressure and air density. Air pressure and air density. Air pressure and air density play a crucial role in how the atmosphere behaves. Gravity keeps air molecules close to the Earth's surface, making the air denser at lower altitudes. This means that as we go higher, air density decreases. So to explain further, weight is the force of an object experiences due to gravity. We calculate it using the formula weight is equals to mass times gravity. Meanwhile, density refers to how much mass is present in a given volume, and it is calculated as density is equals to mass over volume. So near sea level, air density is about 1.2 kilograms per cubic meter, meaning there are more air molecules in a given space compared to higher altitudes. Now, we will move on to air movement and air pressure. So air molecules are always in motion. When they collide with objects, they exert their forces that could combine to create air pressure. We define pressure as force per unit area, or pressure is equals to force over area. At sea level, the atmospheric pressure is about 14.7 pounds per square inch due to the weight of air above. So changes in air pressure occur when the number of air molecules in a column of air increases or decreases. So this is the figure 1. Both air pressure and air density decrease with increasing altitude. The weight of all the air molecules above Earth's surface produces an average pressure near 14.7 pounds per square inches. Now, units of air pressure. So these are the common units for measuring air pressure. First, one will be the millibar. It is used in weather maps. Second will be the hectopascal. It is the preferred unit in modern meteorology. It is also equivalent to 1 hectopascal is equal to 1 millibar. And lastly, will be the inches of mercury. It is traditionally used in aviation and weather reports. Now, let us proceed to atmospheric pressure and its effects. At sea level, standard millibar, or it can be also 1.013.223 hectopascal or 29.92 in inches of mercury. So air pressure affects us in different ways. For example, when we might experience a popping sensation in our ears, this is because of the difference in pressure inside and outside our drums. And it is important to remember that air has weight. In fact, the total weight of Earth's atmosphere is around 5.08 times 10 to the power of 14 kilograms. Atmospheric pressure and elevation. As we go higher in elevation, atmospheric decreases. It is because there are fewer air molecules at higher elevations. And a simple rule is that pressure decreases by about 10 millibar for every 100 meters or 320 feet of elevation. At around 5.5 kilometers or 3.5 miles above sea level, atmospheric pressure is about 500 millibars, meaning half of the atmosphere's molecules are below this level. And at the summit of Mount Everest, 9 kilometers or 29,000 feet, pressure is about 300 millibars, with nearly 70% of atmospheric molecules below this point. And the atmosphere extends hundreds of kilometers upward, gradually becoming thinner until it merges with outer space. This will be the figure 1.10. It is the atmospheric pressure decreases rapidly with height. Climbing to an altitude of only 5.5 kilometers where the pressure is 500 millibars would put you above one-half of the atmosphere's molecules. This is also the figure 1.11. It is the layers of the atmosphere as related to the average profile of air temperature above Earth's surface. The header line, which is the red one, illustrates how the average temperature varies in each layer. So now let us explore the layers of the atmosphere. Unlike air pressure, which steadily decreases with altitude, air temperature changes in different patterns, leading to the division of the atmosphere into layers. First layer of the atmosphere will be the troposphere. It is the lowest atmospheric layer where weather occurs. Here, temperature decreases with altitude at an average lapse rate of 6.5 degrees Celsius per 1,000 miles or 3.5 degrees Fahrenheit per 1,000 feet, which is seen earlier in figure 1.12. So the tropopause marks the boundary between the troposphere and stratosphere, and its height varies. One will be the higher in summer and at equatorial regions due to warm rising air, and lastly lower in winter and at higher latitudes due to colder and denser air. And also, tropopause separates the troposphere from the stratosphere. Next one will be the stratosphere. Stratosphere initially temperature remains constant in isothermal zone before increasing height. The ozone layer in this region absorbs UV radiation, causing warming, and this warming effect prevents weather from occurring here. Third layer will be the mesosphere. Here, temperature decreases again with altitude. It is the coolest atmosphere layer in which meteors burn up in this layer due to friction with air molecules. the air feels cold due to the low density of air molecules. And here is where auroras, the northern and southern lights, occur. Now we will proceed to the jet streams and temperature inversions. Jet streams are strong, narrow air currents found near the tropicals, and it is moving at speeds exceeding 100 knots or the 185 kilometers per hour or 115 miles per hour. And in the temperature inversions, it is occur when air temperature increases with height instead of decreasing, disrupting normal weather patterns. And the implications of the lapse rate in the figure 1.12, it shows how the temperature lapse rate near Earth's surface is about 3.5 degrees Fahrenheit per 1,000 feet. Example for this, if surface temperature is 46 degrees Fahrenheit, at 4,000 feet, the temperature would be near freezing, which is 32 degrees Fahrenheit. And this explains why snow and ice form on mountains even when lower elevations are warm. So this will be the figure 1.12, stating that it is the near Earth's surface, the air temperature lapse rate is often close to 3.58 Fahrenheit per 1,000 feet. If this temperature lapse rate is present and the air temperature at the surface is 0 feet, is 468 Fahrenheit weather, the air temperature about 4,000 feet above the surface would be at freezing, and snow and ice might be on the ground. So now we will now proceed to the atmospheres of other planets. First one will be the Venus. In Venus atmosphere composition, there are 96.5% carbon dioxide with some water vapor and nitrogen. In the cloud cover, it has thick sulfuric acid clouds obscure the surface and trap heat. In Venus surface pressure, it has 93,000 millibar over 90 times greater than Earth's pressure. In Venus temperature, it has 460 degrees Celsius or 860 degrees Fahrenheit, making it hottest planet or hotter than Mercury. And lastly, for the weather of the Venus, it has a strong winds which has a 320 kilometers per hour or 200 miles per hour. And the dense atmosphere create a runaway greenhouse effect which cause trapping extreme heat. Next one will be the Mars. So in the atmosphere composition of Mars, it has a mostly carbon dioxide with traces of other gases, dust, and water vapor. And it has a 6 millibar, less than 1% of Earth's pressure in the atmospheric pressure of Mars. And when it comes to the temperature, it averages -55 degrees Celsius or -67 degrees Fahrenheit with large variations due to thin atmosphere. When it comes into the weather of the Mars weather, first, the heat escapes quickly, making nights extremely cold. It has also an occasional clouds, dust storms, and thin frost layers which have been observed. And lastly, when it comes to the weather of the Mars, the heat escapes quickly, making nights extremely cold. In occasional clouds, dust storms, and thin frost layers, this have been observed. And it has also a hurricane scale, dust storms that can cover the planet for months and leaving reddish haze. Next one will be the Jupiter. Jupiter, it has mainly hydrogen, helium with traces of methane and ammonia when it comes in atmospheric composition. In weather, it has a great red spot. It is a massive storm that is 3 times size of Earth, spinning counterclockwise for at least 350 years. And it has an intense lightning and fast-moving storm bands occur unlike Earth's weather. When it comes to cloud bands, Jupiter's rapid rotation steers the upper layers and forming horizontal cloud layers of different colors. Lastly, the other gas giants, which are the Saturn, Uranus, and Neptune. First one will be the Saturn. It has a similar storm systems exist with swirling bands of gas. The Uranus and Neptune has a cold atmospheres mainly composed of hydrogen, helium, and methane. And lastly will be the Neptune. It has a strongest winds in the solar system, reaching 2,100 kilometers per hour or 1,300 miles per hour. So this will be the figure 2, the Martian sky and landscape, photographed by the Spirit robotic rover during April 2005. So this will be the figure 3, an image of Jupiter and the vivid cloud bands and swirls in its atmosphere, collected by the Hubble Space Telescope in April 2014. Now we will now proceed to the radiosonde. A radiosonde is a small, lightweight weather instrument attached to a balloon that measures temperature, pressure, and humidity at high altitudes, up to 30 kilometers or 90 miles. And it is also transmits data back to the surface and helps scientists study vertical atmospheric profiles. So this is an image of the radiosonde with parachute and balloon. So the radiosonde contains a thermistor. It is to measure temperature. Second one will be the carbon. It is coated plate to measure humidity. And lastly, a small barometer. It is to measure air pressure. So as the balloon rises, the radiosonde sends data. Eventually, the balloon bursts and the radiosonde descends with a parachute. So the radiosonde operations are: it launched twice daily worldwide. Second, it is expensive because many radiosondes are lost or damaged. And lastly, it is complemented by satellites which provide vertical temperature profiles for remote regions. So now I will now give the floor to Ms. Lorian to discuss the weather and climate.
So we will now be defining weather and climate. So when we talk about weather, it is the condition or atmospheric condition in a certain place and time. So today, what is our weather for today, Kai?
It's a rainy day.
Yes. Then we have air temperature. Air temperature is the degree of hotness or coldness of the air. Air pressure is the force of the air above an area. Humidity, a measure of the amount of water vapor in the air. Clouds, the visible
the meteorology. So, meteorology. What is meteorology? It is the study of the atmosphere and its phenomena. So, the term traces back to Aristotle, who wrote Meteorologica. So, these are the inventions in the development of meteorology as a science began in the mid-14,000s. First would be the hygrometer, which measures humidity. Second one will be the thermometer. It is invented late 15,000. Third one will be the barometer, which measures air pressures. And during 18,000s, advancements in instruments improved in this year for forecasting. In 1843, the telegraph enabled faster transmission of weather observations. During 1869, crude weather maps using isobars or the equal pressure lines were developed. In 1920s, air mass and weather front theories were formalized in Norway. During 1940s, the upper air balloon observations provided 3D atmospheric data. In 1950s, scientists developed mathematical equations to describe weather. This led to numerical weather prediction with high-speed computers. In post-World War II, surplus military radars were adapted for meteorology. In 1960, the first weather satellite, which is the TIRAS-1, was launched, and it improved forecasting with satellite images. In mid-1990s, Doppler radars replaced older radar systems. It is to detect storm structure, wind patterns, and precipitation intensity. So this will be the satellite image that shows the dynamic nature of the atmosphere as ribbons of water vapor, or the gray regions swirl counterclockwise about huge storms over the North Pacific Ocean. Also, this is a Doppler radar image showing precipitation over portions of Indiana. The areas shaded light green indicated lighter rain, whereas yellow indicates heavier rain. The dark red shaded areas represent the heaviest rain and the possibility of hail and intense thunderstorms. Now, I will give the floor to Ms. Ward.
Our next topic will be a satellite's view of the weather. Since we have discussed what is the definition of climate and weather, we will now be delving deeper into the different types of weather in the Earth. Now we have figure 1.16. So this figure is a satellite image taken in visible reflected light. This image shows a variety of cloud patterns and storms in Earth's atmosphere. So we will be further discussing the weather patterns that is happening here. So we have geostationary satellites provide continuous monitoring of weather patterns from about 36 kilometers above Earth. So these satellites were the one responsible in capturing this image. So satellite images reveal cloud formations, storm systems, and other weather features. Meridians are the longitude, thin solid black lines from the north to the south. At parallel of latitude, we have from the north to the south. That is what we call the longitude, and the latitude, which is the from there to there. Solid black lines that are parallel the equator. So the latitude of the equator is 0 degrees north pole, which is 90 degrees north, and that of the south pole is 90 degrees south. So the We have middle latitude cyclonic storm system. It's what we call the extratropical cyclones. So this is an image of a middle latitude cyclonic storm system. It is a large organized cloud masses with counterclockwise rotation in the northern hemisphere associated with fronts. Then we have hurricane. Hurricane or intense tropical storm with swirling clouds, high winds. It is 65 knots or more and has a calm eye at the center. So you may ask, what is the difference of a hurricane and a cyclonic or a middle latitude cyclonic storm system? So a hurricane or tropical storms that form over the North Atlantic Ocean and Northeast Pacific Ocean, while tropical cyclones are formed over the South Pacific and Indian Ocean. So their difference is where they are formed. So they are called middle latitude cyclonic storm system or hurricane. Then we have thunderstorms. It is a calm, churning clouds with lightning, thunder, strong winds, and heavy rain, often appear as small white spots on satellite images. Then we have tornado. It is an intense rotating column of air extending from a thunderstorm to the ground, more than 2 kilometers or 1.2 miles in diameter, can be extremely destructive. Then we have here a weather map. We will further explain what is happening here in our weather map. We have here the cold front, the warm front, the stationary front, the occluded front, thunderstorm, light rain, rain shower, wind direction, and wind speed. We have the highs. We have also here a weather map. So we have the highs or the anticyclones, regions of high atmospheric pressure associated with clear skies and fair weather. Wind blows clockwise and upwards. As you can see here, we have this color and it is labeled as H. Para mas makita here, the dark blue ones, that is our highs. Then we have those regions of low atmospheric pressure associated with clouds and precipitation. Wind blows counterclockwise and inward. So this is our highs and this is the counter. So we have the counterclockwise, which is the lows. Then we have precipitation, shown as shaded areas on weather maps, often associated with low pressure systems and fronts. We have here our shaded area, yellow and green. That is our precipitation. Then we have storm movement and evolution. So storm systems are steered by upper level winds. They can weaken or intensify as they move. Hurricanes weaken over cooler water. Thunderstorms can develop and dissipate quickly. Then we have weather and climate in our lives, which will be discussed by Bsedsci.
So now let us proceed to the weather and climate in our lives. So weather versus climate. When we say weather, weather affects daily choices. For example, like clothing or activities. When we say climate, it influences long-term decisions like types of crops grown. So weather determines crop survival, while climate affects crop selection. So these are the impacts on comfort and health. First one will be the cold weather. Wind chill makes temperatures feel colder, and it can lead to frostbite or hypothermia if not dressed properly. Next one will be the hot or humid weather. Here, it often feels uncomfortably warm due to humidity, and heat exhaustion or heat stroke can occur, especially in vulnerable individuals like elderly feel more pain with rising humidity. Heart attacks are more likely in temperature extremes due to blood vessel changes. Third one would be the stroke. Stroke risk increases in high pollution periods. Headaches are common on hazy or overcast days. And some people feel moody or depressed in warm or dry winds or the Chinook winds. Now, let us proceed to the economic and social effects. First one, cold waves during 2013 to 2014, 2014 to 2015. During this year, it increased heating costs, and winter storms or the power outage, business closures, and infrastructure damages happened. This is an image of an utility workers in Maine clear of broken tree branches from power lines during a major ice storm on December 12, 2008. So, tornadoes, hurricanes, and blizzards cost millions in repairs and disaster relief. The droughts and heat waves, crop failures, higher food prices, and possible famine. During 2012 in U.S. drought, widespread crop losses due to high temperatures and low rainfall. So this is an image of a resident of Long Beach, New York. Digs sang out from around his car after Hurricane Sandy pushed water and sand far inland in October 2012. It destroyed homes, commercial businesses, and approximately 10,000 cars in this area alone. Let us talk about the financial impacts of extreme weather. First one is the cold waves during 2013 to 2015. Higher heating cost happens in winter storms, power outages, business closures, and infrastructure damage also happen. The tornadoes, hurricanes, and blizzards millions in repair and disaster relief costs. So this is an image of lightning flashes inside a violent tornado that tore through Joplin, Missouri on May 22, 2011. The tornado ripped through a hospital and destroyed entire neighborhoods. This is also an image of an emergency personnel walked through a neighborhood in Joplin, Missouri, damaged by a violent tornado with winds exceeding 174 knots on May 22, 2011. These are the extreme weather events and their impacts. First one will be the droughts and waves. In California, during 2011 to 2016, billions in crop losses. 1986, Georgia heat wave, 500,000 chickens died. Increased wildfire risks, water rationing. And during 2011, in U.S., drought killed millions of trees and grasslands. So these are the residents evacuate an apartment complex in the Houston area on April 18, 2016 as torrential rains from severe thunderstorms produced severe flash flooding. More than 1,000 high water rescues took place. The tornadoes and severe thunderstorms. This is an image that estimates the lightning strikes Earth about 40 to 50 times every second. More than 20 million lightning strikes hit the United States in a typical year. Here, lightning strikes the ground and buildings over Phoenix, Arizona. So in weather-related damages and forecasting, the annual costs of weather-related events tens of billions of dollars. In hail, it causes 1 billion plus in crop or property damage yearly in the US. So, I will now also, give the floor to Ms. Lorian to discuss what is a meteorologist.
So earlier we have discussed the importance of scientific method in our atmosphere. Now let us tackle or know who are these people that studies our atmosphere. We have what is a meteorologist, or what are their classifications to be considered as a meteorologist. So a professional meteorologist requires a college degree in meteorology or atmospheric science with a strong foundation in mathematics, physics, and chemistry. They use scientific principles to explain and forecast atmospheric phenomena. So its job distribution is approximately half of the United States meteorologists work in weather forecasting. The other half are involved in research teaching or consulting. We have research meteorologists investigate diverse areas like climate change, snowflake formation, and pollution's impact on temperature. They often use supercomputers to simulate atmospheric behaviors and collaborate with other scientists. So, a climatologist is a type of meteorologist who studies long-term climate patterns and the interaction between the atmosphere and other systems like the ocean. So services provided, we have meteorologists provide weather forecasts to the public and specialized services for various actors. We have private weather firms create forecasts and graphics for media outlets. We have newspaper, TV, and the internet. Then we have career information. The passage recommends the American Meteorological Society or AMS website for further information on meteorology. So that would leave us to the end of our discussion for chapter 1. I am Lori Rosa Timor,
And I am Akisha Silong Taras.
leaving you with a quote saying,
From the intricate dance of atmospheric forces to the shared understanding revealed in a weather map,
we discovered that appreciating the Earth's atmosphere